One of the rules in our proof system is the one that we call conditional proof. It says that given a finished subproof starting with the temporary supposition alpha and ending with gamma, you can derive the conditional if alpha, then gamma. Whenever your aim in a proof is to derive a conditional, you want to keep this rule in mind. Let's go through two examples. I'll start with a pretty simple one. Let's suppose your job is to construct a proof from the premise, if not Q, then P and R, to the conclusion, if not Q, then P. Since the conclusion is itself a conditional, we'll try temporarily supposing the antecedent, not Q, and then deriving the consequent P under that supposition. Because if we're able to derive P under the supposition, not Q, then we can close that subproof and use the conditional proof rule to derive the conditional, if not Q, then P, back in the original column of reasoning where we want it. Now the question just becomes whether we can derive P inside of the subproof. And indeed, it's quite straightforward to do that. From lines 2 and 1, we can derive the conjunction P and R using modus ponens, and then from that conjunction, we can derive the first conjunct P. After closing the subproof, that allows us to derive the conditional, if not Q, then P, at line 5, appealing to the conditional proof rule and the subproof from lines 2 to 4. Now, a slightly more complicated example. Let's suppose that we're trying to derive the conclusion, if P or Q, then not R, from the premises, if P, then not R, and not Q and R. Because the conclusion is a conditional, let's try temporarily supposing the antecedent, P or Q, and then deriving the consequent, not R, under that supposition. To derive not R, we could try supposing R and aiming for absurdity. And you absolutely could do the proof that way, but we get a more elegant proof if we instead plan to get not R by showing that both disjuncts of P or Q lead to not R. This is an appealing strategy because P leads to not R very directly. All we have to do is apply modus ponens to lines 4 and 1, and we get not R straight away. Now we just have to show that not R would also follow if Q were true. To show that, notice that the second premise is the negation of the conjunction Q and R. So once we've supposed that Q is true, if we further suppose that R is true, that gives us the conjunction of Q and R, and hence we get a contradiction. So by reductio, we get not R. That allows us to derive not R under the supposition P or Q using the disjunction elimination rule, appealing to the disjunction at line 3, the subproof from 4 to 5, and the subproof from 6 to 10. Finally, having supposed that P or Q was true in addition to our premises, and having derived not R under that supposition, we can discharge that assumption and conclude that what follows from our premises alone is the conditional statement, if P or Q, then not R.